Next, we're going to state and prove a fundamental theorem about finite fields. The theorem has 3 parts. The first part states that the characteristic of a finite field is always a prime number. Which we always denote by P. And if the extension degree of K over the finite field with P elements, which we denote F sub P, if this degree is equal to F, then the number of elements in K is equal to Q equal to P to the F's power. That is to say, a finite field always has cardinality a power of P, where the exponent is always equal to the extension degree over the finite field with P elements. This part of the theorem is easy to prove. If the cardinality of K is finite, in particular, K cannot contain a copy of the field of rational numbers. So this means the characteristic of K is not equal to 0. Remember, this is based on our discussion at the beginning. If a K is finite, then it cannot contain a copy of rational numbers, and therefore the characteristic cannot be equal to 0. And hence, we must get the second case, that the characteristic must be equal to P. And for the second part of the theorem, we only need to recall the definition for the extension degree. In this case, because F sub P denotes the finite field with P elements, and the extension degree is equal to F. By definition, this means K as the vector space over the field with P elements has dimension F. And every element in K can be written uniquely as a linear combination with respect to a basis of K over the finite field Fp. And each coefficient comes from Fp. So in total, there will be P to the F many combinations. So this implies that the cardinality of K must be equal to P to the F's power. And this finishes the first part of the theorem. The second part of the theorem states the following: that P be a prime number, and let Q equal to P to the F's power, where F's bigger or equal to 1, be a power of P, and let omega be an algebraically closed field of characteristic P. Then there exists a unique subfield Fq of omega, which has Q elements. And this subfield is a set of the roots of polynomial x to q minus x. So the second part of the theorem says that if you are given a algebraically closed field omega of characteristic P, then for any power of P, you can always find a subfield in this omega, and it is uniquely determined by the set of roots of this polynomial inside this algebraically closed field. Now let's prove the second part. If the characteristic of this omega is P, then by the lemma above, the forbiddance map sending x to x to the p will be a monomorphism, or in other words, an isomorphism onto one of its subfields. By this lemma, the map that sends x to p will be a monomorphism, or in other words, an isomorphism onto its image. Now we claim that this map is also surjective, or epimorphism. This is because, by our assumption that omega is an algebraically closed field, omega is algebraically closed, and it follows that the equation x to p minus a equal to 0 for any a in omega always has a solution. And this shows that this map is also surjective. So this map is an automorphism. As a result, if we look at the fth iterate of this automorphism, what is the fth iterate? The fth iterate will be sigma to the f's. Now it sends x to the p to the f. This f iterate is also an automorphism of omega. And by our notation from the second part of the theorem, p to the f is denoted by q. And now we claim that the equation x to the q minus x equal to 0 has q equal to p to the f many distinct roots in omega. And the key word here is distinct. Why is this so? So now let's check the claim. This claim follows from two things. The first thing is that omega is algebraically closed. And the second thing is that if you look at the formal derivative of x cubed minus x, the formal derivative, so this is equal to q x to q minus 1 minus 1. And because q is equal to p to the f, and f is bigger or equal to 1 by assumption. So the first part vanishes. This is just equal to minus 1. So this is because characteristic of omega is equal to p, which divides q. These two together will imply that this equation has q equal to p to the f many distinct roots. You should have learned this from your abstract algebra class. If you don't remember, let me quickly recall how this implies the distinct roots. Suppose this guy has a root of multiplicity at least 2. Say R1 is at least 2. Now, if you look at the formal derivative of it, by the product rule, let's write the derivative into two parts. The first part is R1 times x minus x1 to the R1 minus 1 multiplied by the rest. And the second part is x minus x1 to the R1 times the derivative of the rest. If we factor out a linear factor x minus x1, we see that this is a polynomial x minus x1 times another polynomial. And this guy is either 0 or a multiple of x minus x1. So the formal derivative of this guy cannot be equal to minus 1. So we have a contradiction here. And this contradiction comes from the fact that we assumed that this guy has a root of multiplicity at least 2. Therefore, every root of this guy must be a simple root. And because omega is an algebraically closed field, we know in algebraically closed field, the polynomial equation can be completely factorized. So this guy must have q equal to p to the f many distinct roots in omega. And this finishes the proof of this claim. Now we make the second claim. The second claim that those q distinct roots of the polynomial xq minus x form a subfield of omega. And we will denote the subfield by f sub q. So why is it so? If you have a strong background in abstract algebra, this is immediate. This is because if you look at the collection of the fixed points of this automorphism, this is sigma to the f iterate. And we know this is a field homomorphism. Because this is a field homomorphism, it preserves the sum, product, and the inverses, both multiply inverse and additive inverse. So if we call this guy fq, then you can check that if x and y are in fq, then x minus y is also in fq. And if y is not equal to 0, then x divided by y is in fq. And of course, 0 and 1 are both in here. So this is a subfield. So if you are familiar with the basic abstract algebra, this is very obvious. Okay, now let's return to the statement of the second part of the theorem. We have proved that there exists a subfield f sub q of omega with q elements, q is equal to p to the f, and it is indeed a set of roots of this polynomial. There's one more thing to prove. We want to show that this subfield is actually unique. So why is it unique? Now let's check this, the uniqueness of fq. Now we take an arbitrary subfield of omega with q elements. Then we look at the multiplicative group k star of non-zero elements in K. This multiplicative group has Q minus 1 elements. Therefore, by basic group theory, we know that the order of each element must divide Q minus 1. So x of Q minus 1 must be equal to 1 whenever x is in K star. And thus, for any elements in K, x to Q must be equal to x. Because the additional element from here to here is just 0. And 0 trivially satisfies this. And this shows K must be contained in FQ. Because any element in K satisfies this equation. And if you recall the definition for FQ, it consists precisely of those q distinct roots of x to q minus x. But at the same time, K has cardinality Q. So this forces K equal to F sub Q. Therefore, FQ must be unique. It is the unique subfield with Q elements in omega.